Absolute value inequalities. So an absolute value inequality basically has a less than, a greater than, a less than or equal to, or a greater than or equal to sign instead of an equal sign. So let's talk about what they mean. So the absolute value of x is less than 2 means that I want the distance from 0 to be less than 2. So what we're going to do is first put our boundary lines. So what is exactly 2 away from 0? Well, that would be a 2 and a negative 2. Now, the reason I put open circles is because if it is a less than or a greater than without equal to's, those are always open circles. If it is less than or equal to or greater than or equal to, those are closed circles. So these are our boundary points. That's what these guys are. So these are your boundary. Now we have to decide what else do I have as solutions. Am I going to be shaded inside between the boundaries or on the outside of the boundaries? Well, if I want to be less than 2 away from 0, what else is less than 2 away from 0? That would be a 1 and a negative 1, maybe even a 0 or a half. Okay, so you're shading everything inside of here between your two boundary numbers. So what that means is I can have all of the numbers that are less than 2 and all of the numbers that are greater than negative 2. Both of these, as long as it's in a solution of both, it'll be a solution to the inequality. So here's the deal. If we try to pick something like 4, if we try to pick 4, 4 is greater than negative 2. That is a true statement. However, 4 is not less than 2. So because 4 does not work here, that means this is not a solution to this inequality. So really, the way we can kind of simplify this to write it is we can write the small boundary number, negative 2, is less than x, which is also less than 2. So when you have an and, when you have the less thans, you have to be true for both sides of your inequality. So this right here is a simpler way to say the solution to this inequality. Then if we have the absolute value of x is greater than 2, same idea. We want to be between, the distance between x and 0 is larger than 2. So again, we're going to put our boundary numbers of negative 2 and 2 because those are exactly 2 away from 0. So which numbers are, well, further than that? So that would be something like 3, maybe 4, but I can also have maybe negative 3. That's further than 2 away from 0. So is negative 4. So in this time, you're shading outwards. You're shading away from your boundary, not in between them. So when you're shading away, that means I can have all the numbers that are greater than 2, like 3, 4, and 5, or I can have all the numbers that are less than negative 2, like negative 3 and negative 4. The difference between the two is this one actually says or. So as long as the number you are trying to see is a solution to either one of these, it will work. So negative 3, for example, is a solution to x less than negative 2, but not for x greater than 2. But that's okay. It still falls in the shaded area. Let's say 5. 5 is a solution to x greater than 2, but not for x less than negative 2. So those are both solutions because it at least satisfies one of them. If you try to pick something like 1, let's say, 1 is a solution to neither. 1 is not greater than 2, and 1 is not less than negative 2. So 1 is not a solution. Now, this one cannot be combined. These must be kept separated. You can't combine this into a single inequality because these shades don't overlap. Shades don't overlap. So now let's get into some examples. So when do you use and when do you use ors? So for less than inequalities, you're going to use the word and you can remember this by the end of this guy kind of sounds like the word and. Less than will be an and in the middle. The greater thans, well, if you kind of slow it down, greater than, those are going to use the word or in the middle. So less thans can be combined like this in the end. And greater thans have to be kept separate, okay? So let's look at some examples. These are really basic to help you get the idea of what's going on. So the absolute value of x plus 7 less than or equal to 2. The solving process is still the same. You're still going to split apart the absolute value. So we are still going to have the inside, x plus 7 less than or equal to 2. But when we come over here and do x plus 7 and the negative 2 side, we have to flip the inequality in the center. Whenever you change this guy from a positive to a negative, you have to flip the inequality. So it's no longer a less than, now it's a greater than. So do we use the word and or do we use the word or? Well, the original sign was a less than. So less than, so we're going to use the word and. So that means this has to be a solution to both of these inequalities in order to work. Once you have it split apart, now you can actually go solve like normal. So we're going to subtract 7 from both sides of the inequality, x less than or equal to negative 5. And then we're going to subtract 7 on this side, and we get x greater than or equal to negative 9. The way we can finish this off is we can write the word and in the center, and then this is one way to write our solution. The other way to write the solution is the combined version. So with the combined version, it's a little easier to see with a graph. And we are going to graph all of these on number lines. So I'm going to put 0 over here. This is around where negative 5 would be. Here's around where negative 9 would be. Not drawn to scale, but as long as they're labeled, you're okay. So the boundary numbers, negative 5 has a less than or equal to, so it's going to be solid. Negative 9 also has a less than or equal to, so it's going to be solid. Since it is an and, you are shading in the center. So your final solution to this drawing-wise, the graph, is going to be the shaded all in the center of the boundary numbers. Okay, so when I write this in the condensed version, we're going to have negative 9 less than or equal to x in the middle, less than or equal to negative 5. Both are acceptable answers. You can either write it as two separate inequalities separated by the word and, or all in one like this. Now let's look at number 2. So with number 2, we have the absolute value is less than 0. Let's think of what the absolute value does. The absolute value takes negative numbers and makes them positive. So if I want the outcome to be less than 0, that's telling me that I need the outcome of an absolute value to be negative, which isn't possible. So the answer to this is no solution. You will never have the absolute value of something will never be smaller than 0. Because it always makes positive, and things smaller than 0 are negative. You will never be smaller than 0, no matter what you put in there. And then let's look at 3. So for number 3, we have c minus 1 greater than or equal to 5. So this is a positive number on the outside, so we can solve this just fine. It's not going to be any special solution. So the absolute value of c minus 1 greater than or equal to 5. So the absolute value is alone, so we can go ahead and split this up. So c minus 1 greater than or equal to 5. Then the other one is c minus 1 less than or equal to negative 5. Remember, when you change this to a negative, you have to flip the symbol in the middle. Then we have to decide which word. So this is a greater than, greater. So we're going to use the word or. So that means the shade is going to go away from the boundaries. So here we are. So let's add 1 to both sides. So we get c greater than or equal to 6. Add 1 to both sides. And we get c less than or equal to negative 4. All we have to do is put the word or in the middle, and this is your algebraic solution. We cannot combine this into something simpler like we did for number 1. And then last, make sure you graph your answers on number lines. So we've got 0 in the middle, 6 would be on the right to 0, and negative 4 would be on the left. So our boundary numbers, a greater than or equal to for 6, so solid, less than or equal to for negative 4, so solid. So if I want all the numbers larger than 6, I'm moving to the outside. If I want all the numbers less than negative 4, I'm going to shade again to the outside. And this is the graphical representation of our answer. Let's look at 4. 4 is the last one to get a basic idea of how this works. So for number 4, we have the absolute value of 10 minus m greater than a negative 2. So again, stop and think about what an absolute value does. An absolute value takes everything negative and turns it into a positive. So if we are saying that the result of this needs to be larger than a negative number, that happens all the time, because all the positives will always be larger than any negative number you have. So if you have greater than a negative, the answer to this guy would be your all real numbers. There's infinite solution to this. All the numbers will always be greater than a negative when you have an absolute value. So the absolute value of something is always larger than a negative number, always. Now let's move on to the more complex examples, so ones like you're actually going to see. So if we look at number 5 does not have the absolute value isolated, so we're going to have to manipulate this a little bit before we can split it apart. So first, we're going to have to subtract 1, because addition and subtraction is always taken out first. So 4 absolute value of 2x minus 5 is greater than 20. Divide out the 4 from the front. Dividing by positives do not change your absolute value symbol, so we can leave this as a greater than 5. Now that the absolute value is by itself, we can split this up. So we're going to have the inside, 2x minus 5 greater than 5. Because it's a greater than, this is the or, 2x minus 5 is less than negative 5. Don't forget to flip the symbol. Once it's split apart, we can solve this like normal. So we're going to add 5 to both sides. So we're going to get 2x greater than 10. Divide out the 2. X greater than 5. Then on the right side, you're going to add 5 to both sides. We got 2x less than 0. Guys, that's fine. 0 is a number. So all you're going to do is try to get x alone by dividing by 2. And 0 divided by 2 is still 0. Remember to put the word or in the middle. Drop your or down. And this is the solution to this absolute value inequality. So let's see what that looks like graphically. So graphically, if we plot this on a number line, we are going to have, so we're going to have 0 and then 5. Now that just says greater thans and less thans. So these are open circles this time, just says greater thans and less thans. So I want all the numbers larger than 5. So it's going to be to the right of 5. All the numbers less than 0, that's going to be to the left of 0. And there's your graphical representation. Now for number 6, try to pause the video and get the absolute value isolated yourself. Here's the absolute value isolated. Now with this one, we have to think just a little bit, okay? Because there's a 0 and zeros are weird. So the absolute value larger than 0. Well, that happens all the time. But are you also allowed to be equal to 0? Yes, you can. However, this does not say equal to 0. So your answer is not simply all real numbers. We have to figure out what in here is going to make that guy equal to 0, and we're not allowed to include that number. So if this had been greater than or equal to 0, then you would be completely done, and you would just say all real numbers, because that is always true. But since we're missing this little equal to down here, we have to continue to see what we're not allowed to have. So we're going to split this guy in half. So negative k plus 3 greater than 0. Negative k plus 3 less than a negative 0. Well, negative 0 is still just 0. We still need to flip the symbol because we did take it and switch signs. It's just because it's a 0, you don't really see it. And then because it's a greater than, we're going to use the word or. And we're going to solve these two individually. So we're going to subtract 3 from both sides. We get negative k greater than negative 3. Divide out the negative 1 on the front. Now remember, when you divide inequalities by negatives, the symbol in the middle flips over. So this is really a less than 3. Now let's see the other side. Minus 3, minus 3. Negative k is less than negative 3. I'm going to divide out negative 1. And again, when you divide by a negative, this symbol flips over into a greater than. So these two are actually different answers, k less than 3, k greater than 3. So let's see what this looks like. So this is a perfectly acceptable answer, k less than 3 or k greater than 3, but there's another way we can write it that's a little more accurate. So let's go ahead and graph this guy on a number line. So we're going to have, so here's 0 and here's 3. So we've got the open circle on 3. And on the left one, we have k's less than 3. So it's going to be everything over here. On the right, we've got k's greater than 3. That's going to be everything to the right. So what really happens is you're shaded. The entire number line is shaded, except for that one little number. So your final answer to this is, in fact, all real numbers, except k equals 3. That is the only number you are not allowed to have. I can have every number to the left of 3, every number to the right of 3. I'm just not allowed to actually have 3. So, last two. Number 7. I'm going to help you isolate, and then you're going to finish off 7 on your own. So the first step to isolating is adding 2. So you've got 2/3 times the absolute value of 4v plus 6 less than or equal to 12. Now, 2/3 in the front. Really what you're going to have to do is you're going to have to divide by 2/3. But whenever you divide by a fraction, that's really multiplying by the reciprocal. So on each side, instead of writing division by 2/3, we're going to multiply by 3/2, which is okay. Because if you do 3 times 2, you get a 6. 2 times 3 is a 6, and 6/6 makes a 1. So absolute value of 4v plus 6 is less than or equal to, and then over here, we're going to multiply two fractions together. 12 times 3 makes 36, 1 times 2 makes 2, and 36 divided by 2 makes 18. So now that this is isolated, pause the video, solve this, and graph it on a number line. Both of these solutions are acceptable. You can either have this written in 2 separate with the word and, or you can write it all together in a single inequality. And here's the graphical representation. Pause the video, see if you can try one more completely on your own. Try number 8. And here are your 2 acceptable answers for number 8. You could have either had t less than 3 and t greater than -2/3, or you could have had it all combined into one, -2/3 less than t less than 3. And here's your graphical representation.